In the last lecture, we looked at the electronic band structure of a one-dimensional chain of hydrogen atoms. In this lecture, we're going to continue on in one dimension, but we're going to look at slightly more complicated examples. So if you think about this chain of hydrogen atoms, we saw in the last lecture that we get one band, and the band is half filled, and that would actually lead to metallic conductivity. And we don't normally think of hydrogen as a metal, but at high pressures, let's say like you might find in the interior of a gas giant planet like Jupiter or Saturn, people do think hydrogen would become metallic. But under standard conditions, we would expect a collection of hydrogen atoms to dimerize into H2 molecules. So let's take a look at the band structure of a linear chain of H2 molecules. Okay, because of this dimerization, we now have two different hydrogen distances. We have a short distance here within the molecule, and then we have a longer distance between molecules. And so the unit cell, which is approximately doubled in length, now contains two atoms. It contains the entire H2 molecule. So what are going to be the consequences of this rearrangement of the hydrogen atom positions? The most important consideration is now we have two atoms in the unit cell. Each of those atoms has one orbital, and so there's going to be two bands in our band structure. There's going to be a direct correspondence between the number of atomic orbitals in the unit cell and the number of bands in our band structure. The best way to think about it is just to think about the molecular orbitals of the H2 molecule. We have a bonding molecular orbital, and we have an antibonding molecular orbital. And both of those molecular orbitals are going to give us a band. Let's start with the bonding molecular orbital. Okay, here I've written the block function. The wave function of this band of crystal orbitals is going to be equal to e to the ikx times u of x, where the u of x is our basis set. As I said in the last lecture, the basis set is just the molecular orbitals that we find within the unit cell. And so for this band, u of x is going to be equal to the bonding molecular orbital. We'll call that psi plus. So let's take a look at this crystal orbital at a couple of different k points. Let's start at k equals 0. All right, so here's one unit cell. I'm showing here the bonding molecular orbital. The fact that we are at k equals 0 means that the e to the ikx term is just going to become 1. So what that means is that the coefficient in front of each molecular orbital as we go from unit cell to unit cell is going to be 1. And so the phase of the orbitals will not change from one unit cell to the next. And so here are the first 4 unit cells, but if I were to continue going on to infinity, you would see they all look the same. So because the 1s orbitals all have the same phase, the interaction within the molecule, of course, is bonding, as it must be since that's our basis set, but also the interaction between molecules is bonding everywhere. Now what happens when we go to the edge of the first Brillouin zone if we pick a k value of pi over a? All right. Once again, we're going to start with the same basis in the first unit cell, but because the k is different, that means that the phases of the orbitals are going to be different from one unit cell to the next. And when we have k equals pi over a, we know that that e to the ikx term is going to alternate between +1 and -1, +1 and -1, as we move from one unit cell to the next. And that means the phases of the orbitals are going to be opposite every time we go to a neighboring unit cell. So we get a crystal orbital that looks like this. As before, the interaction within the molecule is still bonding, but now the interaction between molecules is antibonding. And so every crystal orbital for this band is going to lie between these two extremes. knowing the energies of the endpoints is probably enough that we can make a decent sketch of our band that comes from the bonding molecular orbital. What about the antibonding molecular orbital? Well, the only thing that's different is that when we look at the unit cell, now the thing we're going to repeat, our basis set, is the antibonding molecular orbital. So at k equals 0, with the antibonding molecular orbital having the exact same phase from one unit cell to the next, we see that we have an antibonding interaction within the molecule. That was expected. But then also an antibonding interaction between each pair of molecules. We might say this crystal orbital is doubly antibonding, and therefore it's going to have a very high energy. In fact, it's going to be the highest energy crystal orbital in the entire band structure. What about at k equal pi over a? Once again, same basis set. So we start with the antibonding molecular orbital, but now, because of the e to the ikx term, we're going to reverse the phase of the orbital each time we go to a different unit cell. So in the second unit cell, it's got the opposite phase, and then the third unit cell is the same as the first. The fourth unit cell is the opposite phase, and so on and so forth. Now, if we were to analyze the bonding of this molecular orbital, it's still antibonding within the molecule, but now the intermolecular interaction has turned into a bonding one. So this crystal orbital is going to be lower in energy than the one right above it. Now let's take these 4 crystal orbitals that we've sketched out, and let's arrange them from lowest to highest energy. We saw that the bonding MO at k equals 0 is bonding everywhere, both within the molecule and between molecules. So we cannot have a crystal orbital that would be lower in energy than this one. We saw that if we were going to stay with the bonding MO basis, but now go to k equals pi over a, we would retain the bonding interaction within the molecule, but now we've got an antibonding interaction between molecules. So this is going to be at a higher energy. Now, the antibonding band at k equals pi over a is kind of the opposite. Antibonding within the molecule, but bonding between molecules. Now, if we were trying to assess which of these 2 crystal orbitals would be at the higher energy, you should be able to see that this one is at the higher energy because the hydrogen-hydrogen distance within the molecule is shorter than the hydrogen-hydrogen distance between molecules. And then finally, the highest energy crystal orbital that we found, in fact the highest one there is the antibonding MO at k equals 0, because that's going to have antibonding interactions both within the molecule and between molecules. With these 4 crystal orbitals ordered in terms of energy, let's make a crude sketch of our band structure. Let's put first our bonding MO at k equals 0. That's the lowest energy orbital. And then our bonding molecular orbital at pi over a. You can see I've put them where I have on the band structure diagram because k is the x-axis here. Then I can put the antibonding MO at k equals pi over a. As we said on the last slide, that's going to be a little bit higher in energy than the bonding MO at k equals pi over a. And finally, our highest energy crystal orbital, which falls at k equals 0. Now, let's sketch in some lines to connect the points. This would be the band that comes from our bonding MO, and this would be the band that comes from our antibonding MO. Voila, there's our band structure. One more detail that we want to include in a band structure diagram is something to tell us which bands are occupied and which bands are empty. There's an energy called the Fermi energy, or the Fermi level, and what this energy represents is at t equals 0, all of the crystal orbitals below the Fermi energy are occupied, and all of the crystal orbitals above the Fermi level are empty. So in this case, we have a bonding band that's completely filled and an antibonding band that's completely empty. And when you think about this diagram, it tells you why this dimerization happens. If we kept the distance within the molecule to be exactly the same as the distance between molecules, then these two bands at k equal pi over a would be degenerate. They would both have the same energy. So you can see by doing this distortion, which leads to a dimerization, we stabilize some of the crystal orbitals, those that end up in the psi plus band, and we destabilize other crystal orbitals, those that end up in the psi minus band. And that stabilization is only energetically favorable because only the orbitals in the filled band get stabilized. Now, in physics, there is a term for a distortion of a half-filled band that leads to a dimerization, and that's called a Pierre's distortion. We might think of it as the extended solid equivalent of a Jahn-Teller distortion. Now, if we were to do this calculation a little more rigorously, here I'm showing what the band structure of this chain looks like if you use extended Huckel level of theory. And, the details change a little bit. It turns out that the antibonding band is quite a bit wider than the bonding band, and that's because the antibonding orbitals are destabilized more than the bonding orbitals are stabilized. Probably this difference is a little bit exaggerated by the extended Huckel theory. But the basic features are the same. Two bands. The lower band runs uphill in energy from k equals 0 to k equals pi over a. And the upper band runs downhill in energy from 0 to pi over a. And the Fermi level lies at the gap between these two bands. Now, when we talk particularly about semiconductors, there's a nomenclature that says that the filled band, or bands, are called the valence band, and the empty band, or bands, are called the conduction band. And the energy separation between the two is called the band gap. We also see in this drawing that if we had drawn the MO diagram for an H2 molecule, we can really kind of think about at least this density of states plot as being obtained by broadening each orbital out into a band. A little nomenclature is in order before we go further. We've seen in some instances, like the hydrogen atom chain, that the Fermi level cuts through a band, and when that happens, it takes an infinitesimal amount of energy to excite an electron from an empty state to a filled state. That can readily be done just by thermal excitation. And so solids where the Fermi level cuts through a band are in general metallic conductors, while those where the Fermi level comes between bands, they have a much larger energy separation between the HOMO and the LUMO, if you want to put it that way. And those we're going to call semiconductors. If the band gap gets big enough, we might call it an insulator. Now, among semiconductors, we can also talk about those which have a direct band gap and those that have an indirect band gap. And this slide illustrates the difference between the two. So in a semiconductor with a direct band gap, the K point at which the valence band reaches a maximum is the same as the K point where the conduction band reaches a minimum. So the gap between the two is separated by just this vertical arrow. And when you have this, then a photon of light is all you need to excite an electron from the valence band into the conduction band. In an indirect band gap semiconductor, the maximum of the valence band and the minimum of the conduction band are located at different K points. And because of that, for an electron to go from here to here, it needs the energy of the photon to be promoted, but it also needs to change its K vector. And remember, we were talking about the K vector being equivalent to momentum. And what that means for an optical transition is the electron has to change not only its energy, but its momentum. And the photon doesn't have enough momentum to do this. So the change in momentum has to come from a lattice vibration, which we also can call a phonon. For indirect bandgap semiconductors, you need to have a photon of light and a lattice vibration or a phonon all at the same place as the electron. And that makes indirect bandgap semiconductors less efficient at absorbing light. Their absorption coefficients are considerably smaller. In some ways, it's a little bit like the transitions in molecules that might be partially forbidden. So when you talk about optical applications, for example, let's say we're using a semiconductor as a light-emitting diode, it's going to be more favorable generally to have a direct bandgap semiconductor rather than an indirect bandgap semiconductor. Okay, let's finish this lecture by going to another example, a linear chain of fluorine atoms, and I want you to figure out what the band structure looks like. I've given you 4 possibilities here, A through D. One of these is the correct answer. So why don't you analyze this and decide which one of these is correct. And after you've done so, we'll go over the answer. To build up the band structure of the linear F atom chain, it's exactly the same as we did for the hydrogen atom chain, but we just have to think about both the s and the p orbitals now. So let's do the s orbital on fluorine first. It would be bonding at k equals 0 and antibonding at k equals pi over a. We would say that this band runs uphill. What about the p orbitals? Let's first think about the p orbital that is oriented along the internuclear axis. All right, so here I draw the overlap at k equals 0 and k equals pi over a. At k equals 0, we see that if we keep the phase of the p orbital the same in every unit cell, then we're going to get antibonding interactions. So this is going to be at a high energy. But at pi over a, where we are inverting the phases of the orbital every time we move from one unit cell to the next, then the interaction turns bonding. And the energy of this band is going to drop as we go from k equals 0 to k equals pi over a. And at k equal pi over a, we would expect it to actually be below the antibonding 2s. Maybe with the caveat that there's actually a pretty wide energy difference between the 2s and the 2p orbitals on a fluorine atom. And then finally, we have to think about the 2px and the 2py, which are oriented perpendicular to the chain. These orbitals at k equals 0 are going to give a bonding pi interaction, and at k equals pi over a, they're going to give an antibonding pi interaction. So this band is going to run uphill from 0 to pi over a, just like the 2s band. However, the width of this band, how much the energy changes as you go from 0 to pi over a, is not as large as the other bands because the pi overlap is going to be less substantial than the sigma overlap. The last thing we need to do to finish this is to draw the position of the Fermi level. Well, a fluorine atom has 7 valence electrons. The 2s orbital is fully occupied. The 2p orbitals are 5/6 occupied. And so 7 electrons is enough to fill up 3.5 bands, right? Because each band can hold 2 electrons. So that means the Fermi level is going to cut about through the middle of that 2pz band. And the other 3 bands will all be below the Fermi level. So this structure, if we could make a linear chain of fluorine atoms, would be a metallic conductor. Now there's one subtlety that I've kind of glossed over here. If you were to do the calculation a little bit more rigorously, what you would find is that there can be mixing between the sigma 2pz orbitals and the sigma 2s orbitals, and that mixing becomes important as the 2 bands approach each other at pi over a. In that approach, they actually avoid crossing each other. So the 2pz band gets some 2s character that raises its energy. the 2ps band gets some p character that lowers its energy, and we get something that looks a little bit like sp hybrids. If you remember correctly, we saw something very similar in the molecular orbital diagram of O2, where we had sp mixing there as well. So to end, let's restate what we've learned from doing the band structure of this linear fluorine atom chain. First thing, now we have 4 orbitals in the unit cell, a 2s and 3 2p orbitals, and so we're going to have 4 bands in our band structure. By drawing out the sketches at k equals 0 and k equals pi over a, we can find that one of the bands, the 2pz band, runs downhill in energy, and the other 3 bands go uphill in energy. We see that the pi bands, for the 2px and the 2py, are more narrow than the sigma bands because the overlap is less. And then finally, we also have to take into account the fact that the atomic orbital energy of the 2s is quite a bit below that of the 2p. And so that also plays a role in deriving our band structure.